Hi everyone. If you have been following my channel in the past several months, I've been posting a couple of videos showing ray traced voxels. 6 months ago, I wrote my first ray tracing implementation in OptiX. It operated on a triangle mesh. It used voxels and also triangles, and I tried to experiment with denoising. It used path tracing for global illumination, and I got to what's called temporal filtering, and I didn't really get much farther. And a couple months ago, I started researching it a little bit more. I tried to do a ray marching application that had global illumination using CUDA, and that worked strictly off of voxels. It used a combination of rasterization, splatting, and ray tracing to do the rendering, and then just ray marching or ray tracing to do the lighting. And that worked. It worked okay, but again, I ran into the issues with the denoising. So upon release of the Quake 2 RTX demo that showed real-time path tracing, I got pretty inspired and found out that the algorithm, thanks to someone named Mikola, was called basically adaptive spatial temporal variance guided filtering. And what that is basically a denoising algorithm. Now I am running this. It is 1280 by 720. It's one sample per pixel, and it's using a voxel resolution of 2048 by 1024 by 2048. And this is done entirely in real time. It averages about 55 frames per second. Um, it's okay. It's very unoptimized at the moment, and it could be done a lot better. But right now, I'm focusing just on getting the functionality down. And the look is to get basically one solid color per voxel and have it handle diffuse lighting, reflections, specular highlights, all that really good stuff that path tracing enables. And so, anyway, when I found out about the A-SVGF paper, I found out about the SVGF paper. And before I go further, like I said, I am running this on an RTX 2070, and you're probably familiar with the AI-based denoiser that NVIDIA has. And I'm not going to showcase it in this demonstration, basically because I have it disabled, even though I can toggle it here. I don't have a way to render it. Um, but the AI denoiser doesn't really work on this type of scene. I'm guessing because it wasn't trained to trace voxels, trace and denoise voxel tracing, and so the result actually looks extremely poor. And so what I've done here is I've actually implemented kind of a hybrid between spatiotemporal variance guided filtering and the adaptive version of it. Oh, I'm sorry if you just heard that noise. I hit my microphone cable. I edit with virtual dub, so I don't know if I'm going to be able to really mute that. But anyway, when I say hybrid, I mean I took stuff from the SVGF paper and then, well, really everything from the SVGF paper, and then started to do the adaptive part of it. And what the adaptive part is, I'll go into a little bit farther. Um, but spatial temporal variance guided filtering basically is three parts. They showcase it in a couple of videos showing their three parts, but it's a spatial temporal filter. A spatial filter is basically a blur, and this would actually be a good time for me to demonstrate what all of these are. So right now I'm using spatial filter, a temporal filter, temporal anti-aliasing, and yeah, those are the three main parts. So this is what it looks like with one sample per pixel. It looks awesome. It has downsides, which I'll get into in the future, ways that I'd like to improve it and ideas that I have. You can probably pick up on a few already. Um, but I'll start by turning these features off one by one. So uh, I have, by the way, I had it with two bounces. So one bounce to trace to another voxel, or another bounce to find out the bounce diffuse lighting. So, but I'll try to touch on that if I remember later on. But right now, this is using. So this is the one sample per pixel input. As you can see, it's very noisy, totally unusable. It uses what's called Monte Carlo sampling, which means every single frame it traces a new ray that's basically bounced in a random direction, and the randomness is weighted based on the normal. In this case, I'm using one normal per voxel, and the result is accumulated over time. In this case, it's not accumulated over time. That's what the temporal filter is. Or rather, that's part of the temporal filter. So it has none here. That's actually the temporal filter applied, but the way a temporal filter works, if you're not familiar, is when the camera moves, obviously, let's say the voxel that my cursor is pointing at right now is not going to be in the same position. So I move to the left a little bit, the voxel moved to the right. Temporal filtering will allow blending samples across frames even with movement by using motion vectors and reprojecting the samples from the previous frame onto the samples of the current frame. And that's really easy if you're just doing camera movement. All you do is just take the view and projection matrix in the last frame, use that to reproject the samples across or into the current frame. There's your motion vector. You don't even have to handle anything else. Of course, with doing that, you run into issues where in the distance I have aliasing due to there being a high density of voxels, and well, you have to test for consistency. And the easiest way to test for consistency is to see if this voxel ID matches the reprojected voxel ID. And if it doesn't, we call that a disocclusion. And a disocclusion is a new pixel in the frame that doesn't have any samples. It was not able to successfully reproject samples from the previous frame. You can use the depth buffer, the normal buffer, any properties that you have besides the mesh ID or the voxel ID or the primitive ID to compare the validity of samples. In this case, I'm using a very weak depth buffer test. So you can see where it fails and where it succeeds. Stuff in the background here, it's noisy where it fails, but it's relatively smooth where it does pass. And of course, you can adjust that. I haven't been able to tweak it to work properly. As it is, it works okay. I don't think I'm going to be able to get distant voxels working perfectly. And so I've come to the conclusion that I'm probably just going to resort to using fog or something to kind of cover that up until I can come up with a good way to test samples based on their depth. I lost my train of thought. I apologize. But another challenge with that is, so this temporal blend factor, it's actually called alpha typically, and alpha controls how much of the previous frame blends with the current frame. A high alpha, like 0.85, means it'll use 85% of the current sample and 15% of the previous sample if it does pass to blend. Obviously, that's totally unusable. Anything really under 0.25 is unacceptable. It doesn't really do a whole lot. So the way that you combat that is when your temporal filter fails, you use a spatial filter. And a spatial filter is basically a blur, a Gaussian blur across the screen, and it uses what's called an edge stopping function, which means it's not going to bleed this voxel here onto the voxels behind it, because obviously that would be it would break the depth. The samples would bleed over the edge. The normals don't even pass. They don't match at all. And so there's a paper called Edge Avoiding A-Strauss Wavelet Transform for Fast Global Illumination Filtering. And that's basically the edge stopping blur using differences in depths, or I think it actually uses sample world coordinates, normals, and luminance. Luminance plays a relatively important part, and that's where the variance guided part of the Spatial Temporal Variance Guided Filtering paper comes into play. I'll try to touch on that a little bit more later, but I'll go ahead and activate that now. And I have it titled A-SVGF, and A-SVGF, like I said, it's really SVGF with some parts of the A built into it. So I was talking about the alpha. If you have a low alpha, like 0.1, it's going to work pretty well. Like, obviously, it's noisy, but it's passable for where the samples line up properly. But if you just use 10% of the current frames, it's going to take 10 frames for those 10 samples to properly average to what they should be. It's going to be using the majority of the first frames, which oftentimes are not accurate. And so the whole point of the alpha is to use what's called a moving average. So the more samples there are, it averages with the previous samples. And the way that we can make that better is use a dynamic alpha value. The SVGF paper doesn't use a dynamic alpha. I think it uses... Now, the paper says that they use 0.2 for the moments filtering. I'm not going to get into the moments. I'm probably not going to touch on luminance too much, but they say they use 0.2. In the source code implementation that they use, they actually use 0.5 or something ridiculously low. But anyway, I use a history guided or like a frame count way of controlling the alpha factor. That's kind of what the A in A-SVGF does, but not entirely. So I'll move on from the temporal filter now and go back to the spatial filter. So when the temporal filter fails, it relies on a spatial filter, which, like I said, is basically a really wide blur. And this looks awesome. It's borderline perfect for the most part. There are, as you can see here, there's some flickering. If I go and there's some disocclusions, it might take just a moment to gather the appropriate samples. This is actually better demonstrated without the temporal filter. So this is what the spatial filter looks like alone with no temporal filter. I'm going to be honest, it doesn't look too terribly bad. Yes, it's flashy. We can improve that with the temporal filter, or temporal anti-aliasing, which is basically a temporal filter. And it looks great until the camera moves, because once the camera moves, it throws away every single sample that there is. So combined, the two end up looking really good. And I use a point... Did I say 0.5 earlier that they use? They use 0.05. So that's what I'm using here. 0.05 works really well. And like I said, it doesn't really matter too much. Just for general camera movement, what low your alpha value is, because the samples are going to converge properly and they get reprojected. You're not going to have dynamic updates in the scene, so it doesn't matter how low it goes. But obviously, if you have moving objects, you delete blocks, you place lights, you move lights, you change your sunlight, you're not going to want to keep as many of the old samples. And the adaptive part of A-SVGF aims to improve that by using a blurred gradient field, is what it's called. But yeah, so this is basically the bulk of the paper. And so that's the spatiotemporal filter. The variance guided means basically it blurs less in regions of high, regions of high sample consistency or high brightness values, and then blurs less in regions with lower sample counts or lower brightness. And the idea behind that is to not overblur shadows. And on the surface here, the samples are mostly consistent, like it's almost all white with a little bit of these colors, by the way, are the second bounce. They're the light bleeding from the other colors. If I turn on the albedo blending, it's not too terribly obvious, but that's what's going on. And again, I lost my train of thought, so I apologize. I kind of figured that was going to happen a bunch in this video. So yeah, this works pretty well. As far as the variance goes, so there are 3 edge stopping functions, C, N, and Z. And they control how strict samples can be blurred across each other. C is related to the variance, N is related to the normals, Z is related to the depth. I introduced my own weight here called P, and that is whenever the depth from the camera to the voxel is less than 64, it applies a strict weight that is guided by the difference in the voxel IDs. So The reason for that is it's probably not going to be too terribly obvious on video, but if I bring that down to 0, the voxels up close don't become very distinguishable. Like there's some voxels right here, but they look pretty blurred together. If I use an edge stopping function, you can make them out a little bit more, and so it just produces a cleaner result. And obviously we don't want to use that for the distance, which is why I only do 64 or less. But going back to the variance and the temporal filter, using 0.1 in bright scenes works pretty well, or 0.5, 0.1 for the temporal blend. However, let's go down to a darker area here. We can see a lot of flickering, and that's because this is going to make them so the samples don't bleed together very much, because they have a relatively low variance. And so by introducing temporal anti-aliasing, that fixes that. Temporal anti-aliasing is basically blending across frames. And so those three major components put together, this, by the way, is a reflective sphere. I haven't nailed down reflections yet. Without all this filtering, it's supposed to be a perfectly reflective sphere, and it looks great, but obviously it's noisy and we have all the blurring going on, so I'm not sure how to deal with that. So yeah, with these three things, and also I use some depth-based weights for the temporal filtering. I'm not too familiar with temporal filtering. Like I don't even use the jitter. Sorry, I keep calling it temporal filtering. I meant to call it temporal anti-aliasing. I'm not too familiar with how it works. I actually use the implementation from the Quake 2 ray tracing, and my motion vectors are just whipped up based on depth and the camera movement, so I'm not even sure if they're totally accurate. But overall, this is one sample per pixel, so like I said, looks great, but let's get into the problems. The main problem is stuff in the distance flickers a lot, and I already kind of touched on that a little bit. The second issue, and the one that bothers me the most, is it's very, very tricky to see, but when there's a region with a highlight value like this, and a region from the distance that has a low light value, doesn't blend perfectly. So you can see that there's kind of some fireflies going on there. I can increase the strength of the spatial filter, and that helps a little bit. I think it's mostly the temporal filter failing though, so I've been trying to tweak it for days. I can't really seem to get it perfect. I have a couple of ideas for that. The other issue is when this value is too high, when I move the camera down, stuff like right beneath the camera has fireflies. A little bit tricky to see, but that's what's going on there. Obviously, ideas for that are to increase the samples per pixel. So this is 3 samples per pixel. 3 samples is basically perfect. And this is not, by the way, these problems are really not an issue with one bounce lighting, so just straight up ambient occlusion, because there's way less randomness involved, and so the samples converge a lot more quickly. But obviously you don't get all the cool bounce lighting effects if you only do 1 bounce. But yeah, we can increase the effective samples per pixel. That tanks the frame rate. I'm getting like 20 to 30 FPS doing this. And yeah, it's just not ideal. And the other thing is I can take advantage of the history lengths, and so when there are disocclusions, I can shoot multiple rays, so we get mostly 1 sample per pixel, but in certain areas we get higher samples per pixel, so it doesn't affect the frame rate too much. And yeah, I mean that's pretty much it. So here's what I've been working on. Sorry if I rambled. I wanted to try to explain as much as possible because I know that there are probably going to be a lot of people trying to get into ray tracing and not really know where to start. I didn't know where to start, but I got something that works pretty well. I'm not sure if you followed the ray tracing stuff by Sonic Ether. He's made the Minecraft ray tracing mod, and he uses the same filter. At least he did in the video that he posted a couple of years ago. Spatial temporal plus temporal anti-aliasing, and that seems to be the way to do things right now. Unless maybe if NVIDIA's AI denoiser, when it's trained, works a lot better. But yeah, I just wanted to mention as well, for rendering these voxels, I am using OptiX 6. I have my own ray tracing stuff to ray tracing intersections defined in the shader code. So this is actually not RTX accelerated, except for the TR BVH traversal. That is hardware accelerated, and I think the AABB ray intersection tests. So if I were to switch this to triangles, it would run just as well, maybe even a little bit better. Hopefully there are driver and API updates that allow us to use ray AABB testing to accelerate this, or what happens on the RTX side of things to accelerate this further. But anyway, I've rambled long enough. Thank you all for watching. See you next time with hopefully some cooler stuff.